So last time we looked at this stalling and data forwarding unit. This data forwarding unit, the hazard detection unit, we can take care of any data hazard. I said any data hazard except for one specific scenario, this guy. We have a LDR followed by any instruction is using source register as the RD of LDR. Then we are in trouble. So if this is the case, we cannot handle this only using hazard detection unit. So in this case, what do we need to do? We need to use stall. Once we have in the cycle 3, we compare this RD value of LDR with RN and RM, any instruction in ID stage. If they do match, then we are in trouble. So what we do, hold this guy, hold on this instruction, and we're going to move this LDR to next instruction. And then we flush this guy, and that's the cycle number 4. In that cycle number 4, now we have a result of this LDR. We're going to write back into this guy. In the next cycle, when we need this R1, we can forward from here to here. So this is the one cycle of the bubble. When do we need to be careful on this scenario? Only one case, LDR instruction followed by one instruction using LDR's RD as a source, R1 or R3. Make sense? That's the only case we need to fit in the bubble. So that's what we discussed last time in cycle number 6, cycle number 7. So the last item for this chapter 7 is about the branch instruction. So branch. The branch is not determined until the write-back stage of the pipeline. Instructions after branch fetched before branch occur. Because branch instruction, I'll show you later, but branch instruction getting into ID code, we're going to feed in the following instruction. And if the branch taken, all of those instructions is going to go into drain. We have to flush out. So those are the 4 instructions must be flushed. These are the 4 instructions we need to flush if we need to do the branch in here. In this, our architecture, we don't want to wait until the last stage. If we can detect a little bit earlier, then we can flush out a little less number of instructions. That's what we're going to see in this series of instructions. So early branch prediction. So branch in our architecture, we're going to have only 2 cycles of penalty. We're going to detect this branch early enough. And then we need to change a little bit of hardware. Okay, we can talk about that later. And also, in order to make a proper branch prediction, there's several techniques that we can look into. For our class, we're going to look at only 2 techniques. It's called dynamic branch prediction, and we'll look at the 1-bit dynamic branch prediction and 2-bit dynamic branch prediction. And those 2 branch prediction, they maintain the table. Based on my experience, I'm going to predict for the next branch. So 1-bit predictors. So these are the shortcomings, and you will see after this example. So we're going to look at the 10 branch outcomes. T as a taken, 1, 2, 3, 4, 5 taken, and N as a not taken, and then followed by 4 taken. That's the actual branch outcome. We're going to use 1-bit predictor in the second row, and the third row is going to tell us our branch prediction was correct or is incorrect. So 1-bit predictor, if my prediction is right, I'm going to keep my decision. If my prediction is wrong, I'm going to change my mind. That's basically it. You're going to be given the first prediction, okay? So either T or not. So let's say in this time is T. So first, we're going to have a T. This is given value. We good? So my prediction is correct or incorrect? Correct. Therefore, I'm going to keep it. Correct. 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 Keep it. Wrong. Incorrect. So at this time, I'm going to change to taken to not taken. And again, this is wrong because I predict as a not taken, but it was an incorrect prediction. So I want to change my decision again to taken, correct, taken, correct, taken, correct. So in this case, it is accuracy of 80%. Copy this down. And I want you to try this second table. So for the second table, we start with the T. Predicted taken, but actual happen is taken. So this is correct. So I'm going to keep it. But this time it's wrong because actual branch is not taken. So now I need to change that. Wrong again, I need to change that. Wrong again, I need to change that. Wrong again, I need to change that. Wrong, change, wrong, change, correct, correct, keep it, correct. For this time, accuracy is the 40%, way below. If actual branch take not taken, alternate way, then the accuracy is going to be really low. Now, to-be predictor. So in the flow chart of to-be predictor is something like this. I predict taken, it is taken, then I'm going to stay in here. However, predict is taken but not taken, I'm going to predict taken again. So basically, until I guess wrong twice in a row, we're going to keep my decision. Okay? So let's do this. So this time, I'm going to start with the N, not taken. And it's something like this. And then first prediction, wrong, incorrect. Still, I'm going to keep it. But now I have twice in a row, I predict wrong. Therefore, I need to change my prediction as a taken. Correct, 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 correct. Actual branch is not taken, but I predict taken. Incorrect. However, this time, I'm going to keep it because this is only once I mispredict. So I'm going to keep it as a taken. Then we have 70%. Now in the second table, just like what we saw in the previously, taken and not taken is alternate way in the beginning. So start with the not taken. My prediction is wrong, but I'm going to keep it one more time. But this time is correct, so I'm going to keep it. Wrong. This is the first time, right? It's not twice in a row. So I'm going to keep it. Now it's correct. So I'm going to keep it again. And incorrect. But I have to keep it because it's not twice in a row. And so it's correct now. So I'm going to keep it. Incorrect. Incorrect. Now, because I have twice in a row, it's incorrect. So now I need to change as a taken and taken. So in this case, it's a little bit approved of the accuracy. So now let's look at the pipelining. So I gave you another handout, so that's something you want to copy down. So this is the pipeline processor with the early branch target address. So this is the typical architecture, the actual branch happening in the fifth cycle. So we need to look at the control, stalling logic, and once we go through the diagram, it's going to be all clear. So I don't want to go through any of this. Here's the series of instructions. Cycle number 1. As you can see, the first number is the instruction memory address, instruction address, okay? 20, 24, 28, 22C, 30. The first instruction, 20, branch always with the 2. And when you get to this, PC value is a 20. PC plus 4 is 24 in hexadecimal number, right? That's this cycle number 1. Yeah, these are the PC values, address of these instructions. That's a good question. Let's start with this. So we have this series of instructions. We're going to have 20 branch always. We typically had the letter go 1 or something, right? But instead of using the letter, I'm going to just use 2, meaning where's the PC plus 8? Here's the PC. Where's the PC plus 8? 28. And we need to go 2 lines below. So 1, 2. So we're going to go in here. That's what we want. Based on that, we should be able to calculate this number. PC plus 8 and 2 lines below. Are we good? Okay. And then in the cycle number 1, we have PC value right here as a 20, and then PC plus 4 is a 24 after we add 4 there. And then cycle number 2, this branch always in the ID stage. Now we're going to select 15 because it's the branch instruction. And we're going to have this value that is 28. Why is 28? Because PC plus 8. And this is also 28 because we are reading content of R15. Yeah, this is the IF stage and this is ID stage. So I'm just saying 28 happening ID stage. Right there, it's PC plus 8. Of course, we have PC plus 4 in the AND instruction. Now we're going to get into cycle number 3. Branch always is in the execution stage. And what happened here? What's 8? That is this guy. Branch instruction is the only instruction we're going to go through sign extended in this unit. And plus, we're going to shift left by 2, meaning what? We're going to multiply whatever the value we actually put it in here times 4. Why? Why times 4? Yeah, it's a left shift by 2. But why? Why we want to do left shift by 2? Basically multiply by 4. PC plus 8 was taken care of in here already. So PC plus 8, we fit in. PC plus 8 was 28 because it was a PC value 20. Exactly, again, this memory and instruction memory, these are all 32-bit. How many bytes? 4 bytes. And big endian architecture address is the first byte name, which is 048. Has to be multiple of 4. That's why we have that. And this extend immediate value is going to be sign extended and shift left by 2 for only branch instruction. Make sense? When we have a data processing or memory, all of this is 0 extended and there is no shifting to the left. That's all, nothing, just the 0 extended value to 8, 12. Okay. But for this one, we have a 24 immediate value. We need to shift left by 2 to match up to go to correct instruction address. So that's that. And then we have 8 and the result. Okay, so 28 plus 8 is hexadecimal 30. 8 plus 8 is 16. Hexadecimal 16 is 0, 1 carryover, 0x30. That's the target address that we're going to put it in here. So this is the only case where we have to take the branch. So how do we know? Because branch this guy is 1, and then this conditional unit say, hey, we need to take the branch. The result is going to be 1. That means instead of taking PC plus 4, we're going to take whatever this target address and feed in. Now we have an instruction in here or instruction in here. Then we're going to use the flush. We're going to clean these 2 stages. And the next instruction in cycle number 4, we're going to have an add, which is 30. Make sense? Good question. The question is, these values, this 1, where do we get these 1s from? Nothing happening in here when we get into branch. So we don't know we actually have the branch instruction or not. When we get to this stage, here's the branch. This is D means in the decode stage, E means execution stage, M means memory access stage, W means write back stage. The last letter indicates that which stage in that control line. Make sense? And right now, branch D is going to be 1 based on 32-bit format. We know BAL is the branch. When you decode BAL2 into 32-bit binary, we know it is branch, right? We know based on COND values, based on CMD values, and then based on opcode values. Since this opcode is 1, 0, in this stage we know, hey, this is the branch instruction. And then when you have opcode is 10 plus COND value is 1110, that's the unconditional branch, or all other instructions, right? The data processing COND value is what? 1110. And the memory instructions, COND value is what? 1110. And depends on the conditional. Opcode is 10, it is branch. And we need to look at the table and different values. So for example, COND value is EQ, 0000. That means it is a BEQ. So we have BAL and BEQ. Both opcode is 10 and 10. So that's the same thing. However, when you look at the count value, this one is 1110 and this is 0000. Now, we know this is opcode, so this guy is going to be 1. That's all we know. When you're getting into here, still this branch E is going to be 1. That's why it is 1. And then second value is coming from this the control unit, conditional unit, COND values. It is 1110. That means what? Branch always. So it's automatically flag this as a 1. However, if it was, let's say, BEQ, the COND value is a BEQ, then what? We need to get the result of ALU. Only branch when we have the same inputs, because it is a BEQ. Make sense? So we are waiting for the result of ALU, and they're the same, which means Z value, 0 flag value, Z equals to 1. It is the same value. So then this guy is going to be 1, then branch. If they're not, we're going to have a 0, 1, and 0. It's going to be 0, so we are not going to branch. Did I answer your question? Okay. Yep. Exactly. So the question is, are we subtracting it? Yeah. Always? Yeah. How do you know it's subtracting? Because we have to have another instruction right before branch. What? Exactly. And in the compare instruction, we have only 2 operands. Register, register, register value. So always we subtract. Based on the result, we're going to set up the flag Z, V, C. The last one is N. Based on the subtraction, we know it is a negative, it is a 0, it is an overflow, there is a carry. So based on those values, we're going to send it to here and actually happening. Yep. For the BAL, we don't have to use comp. We could have a comp, but it doesn't matter. We're going to branch always. So when you have opcode 10 and COND value 1110, then it's going to be automatically 1. Oh, ALU control is going to be add, right? Right. So that is controlled by this ALU control. What else? Yeah. Based on this, we know this is branch equal, branch not equal, greater than, less than. I mean, there is a whole series of things. So it depends on those 4-bit values we can have. We need to make a different decisions right there, whether we branch or not branch. Exactly. Based on that, we're going to set either 1 or 0. If it's 1, with 1 and 1, it's going to branch. 1 and 0 is going to be 0. It's not branch. And we're going to just execute the next instruction. Keep doing it. Yeah. When you actually branch is taken, then there's, I mean, it's not showing, but here's the flush control line. And it's flush this guy only. Because now we know the next instruction as a 30. 30 is going to be here in the cycle number 4. This control line is all connected from here. So now we know we have to take the branch. I mean, it's not showing, so don't worry about it. Whenever we have a branch taken, flush this guy, and then the new instruction is in here.